Hi again, everyone. Welcome to our bi-weekly vLLM office hours. We're excited to have you here. Um, we have a great session for you today. We'll be talking about intelligent inference scheduling with vLLM and llm-d. We have a great team here actually to tell you all about that. We have Abdullah and Kaushik from Google, as well as Nili from IBM joining us. I've also seen a handful of their team members and people that are very close to the llm-d project, and we have, of course, join this call. So please feel free to ask any questions, give any feedback. This is a completely community safe open space. We look forward to hearing from everyone. And also we have our own Michael going. I'm sure you know Michael. He's been here with me every single office hours for the last 32. So Michael will give his regular update to start. And then before I pass it over to Michael, if you can just do one more slide, please. So we love keeping these sessions interactive. Please speak up and engage with us. You can raise your hand and start speaking. You can also use the chat. We are live streaming the session on both X and YouTube. We're monitoring both of those chats as well. So if you're on those platforms, just ask, give feedback. We'll make sure to address at the end of the call. This meeting is being recorded. You'll find it on YouTube pretty much momentarily after a few minutes later. So feel free to check it out again and share it with your friends and colleagues. One call out for the vLLM developer Slack. If you're not there, please do join us. Great place to stay up to date with the vLLM and also talk to everybody that you have here on the presenter list. We're all in the vLLM Slack and very happy to engage with the community at any time. And two more things before I pass it over to Michael. Just a few meetups to call out. We have several vLLM meetups happening in the next few weeks. Austin happening next week on Wednesday. Boston happening the day after on September 18th. Toronto happening the following week on September 25th. And then we also have a Melbourne meetup that was supposed to be in October, but we rescheduled it to a few weeks later due to some scheduling conflict. If you are in any of these cities, or if you know somebody who's in these cities, please send them an invite. There's still a few spots left for each of these. We're at wait list pretty much, but we can always accept a few people that join office hours. And two more things again. Now, one thing regarding meetups, if you're ever interested in speaking at a meetup, or if you want to host a meetup in any of your local offices or want to get involved, please reach out to me. My name is Sasha Zelenovic. My name is in your calendar invites all the time. So please reach out to me. We would love to have you support some of these efforts. And one last thing now, before I pass it over to Michael, we would love to know where everybody's dialing from. We usually do this at the start of office hours. You can see the emoji flags on the right-hand side from countries that have joined in the past. So if you can just pull up your chat right now, whether you're on YouTube, on X, or on here, Google Meet, please let us know where you're dialing in from. So yeah, Boston, Canada, Raleigh, North Carolina, is Canada again. Canada again. Whoa, what's going on in Canada? Welcome, guys. This might be the biggest Canada representation so far. Israel, hi, Maroon, good to see you. France, hey, everyone. I hope your race was amazing. Oh, it's actually coming up this week. London, UK, Texas. Hey, Vita. Good to see you. Chris, nice to see you, Chris, from Boston. Cambridge, UK. I see there is a calendar thing. I'll address that right now. So anyway, so welcome, Saudi Arabia. Great, nice to have everyone. Please keep them coming. We would love to add your flag to the emoji list. With that, I'll pass it over to Michael.
Cool. Thanks, Sasha. Happy to see everyone again and be back to office hours. Today, we're going to go over quite a few things in the vLLM community, some blogs, some posts, some really cool things that people have been building on top of vLLM. Unfortunately, no release to go over today, although we will be cutting 0.10.2 and releasing that at the end of this week or Monday at the latest. So fear not, a new release will be out soon with lots of exciting features. As Sasha already mentioned, and you hopefully know, we have a special topic on intelligent inference scheduling with vLLM and llm-d today that our guests will be going over. And in the following weeks, we'll be covering a deep dive into Mamba and hybrid model support, which should obviously hopefully be more important due to some of the state-of-the-art models that are coming out recently, such as Qwen 3 Next. followed by a deep dive into the new vLLM semantic router project, which there should be an announcement over the next couple of days on. Yeah, so to kick us off, if you're not familiar with vLLM, it's the fastest growing de facto standard for open source model serving. It's a very popular open source Apache 2.0 project that's seen consistent growth since it started out as a research paper in the beginning of 2023. So it's had a very rapid 2.5 years of growth, both in terms of usage, adoption by enterprise and researchers, and also in terms of community and the contributors and different institutions that contribute to it. Check out the GitHub here. It's a pip install away or a Docker pull away. And it's meant to be very simple, easy to deploy performantly the state-of-the-art large language models that you're interested in across a variety of hardware. Hopefully you can see some of the various model lists and various hardware supported. And on this slide, I'll sort of dive into that a little bit. So it's a Python-based library that offers an easy-to-use offline inference LLM class and an OpenAI compatible server, effectively trying to match all of the features and application level APIs that you expect from a closed API, but with your own hosted open source models on your own hardware. It supports all the key model families, over 100 different architectures now, from Hugging Face transformers and model scope. It regularly has state-of-the-art inference acceleration research integrated into it because it serves as a very performant inference system base that many researchers fork, publish their papers on, and eventually contributes back as pull requests and things that constantly improve and grow the performance of a complex system like this. It of course gets great performance on NVIDIA GPUs for all those different model architectures, but through the software abstraction that it offers, we're able to support AMD GPUs, Google TPUs, AWS Neuron, Intel Gaudi XPU, Huawei Ascend, all in like production ready large scale deployments, along with many other hardware backends that integrate as plugins in the community. So this is growing day by day. And of course, when I mention model architectures, I'm not just talking about text only large language models, but also multimodal models, hybrid attention models that are using state space models or linear attention, embedding models, so encoder only models and encoder decoder models, reward models as well. So vLLM is heavily used now in the age of RLHF and agents for doing inference rollouts, as now that part of fine tuning and post training is now about half inference and half training. In terms of performance features, there's a lot of custom kernels that we write in vLLM for both unquantized and quantized performance. So we support a variety of model checkpoints in different formats: AWQ, GPTQ, weight-only quantization, also activation quantization at int8, FP8, even the latest formats like NVFP4 and MXFP4 on the latest NVIDIA Blackwell and AMD 350X hardware, and MI350X. And then also other features like KB cache or attention quantization for even more speed up. We write a lot of these kernels ourselves through efficient libraries like Triton or Cutlass, and we also heavily rely on Torch Compile to automatically generate a lot of faster implementations for the PyTorch-based model definitions that live in vLLM and transformers. Now, of course, around the model forward pass itself, we implement many different inference system optimizations like chunk prefill, automatic prefix caching, multi-LoRa batching, speculative decoding, and advanced cluster scale features like disaggregated prefill. which obviously llm-d here is a part of. So you should hopefully learn something about those features today. As I already mentioned, many application level features that you use in the closed source APIs now available in open source, like tool calling, structured outputs, and the responses API. And finally, scaling those model deployments across multiple devices and even into multi-node deployments with a variety of different parallelism features like tensor, pipeline, expert, data parallelism, many of these able to be freely combined with each other for the optimal deployment based on your denser or mixture of expert model deployments. So now that you're familiar with vLLM a bit, now I'll go over some of the latest things in the past 2 weeks. So if you kept up with us in the project, we recently started the recipes subproject. This is a community-driven repo and project where we hope to more clearly document specific model deployment recommendations on a variety of different hardware platforms. So we've been growing this both from existing committers and contributors to vLLM and committers or users of vLLM that want to contribute their own deployment patterns and recommendations for deploying the latest models most efficiently, especially on the leading edge hardware where these things can get pretty complicated. So as you can see now, we have a variety, several different model architectures, almost a dozen now, that are have detailed hardware-specific deployments and recipes. So I recommend you checking those out as it's grown, and offer edits and pull requests directly to the project, and just help us improve the documentation around model deployments. Next, I'll start out with a really cool blog that was done by a great person in the community. Sorry, let me pull up his name here, make sure I don't butcher it. Aleska Gordic. He reached out to us and did this amazing blog himself on the anatomy of vLLM, and then we worked with him to get it on the official vLLM blog. So definitely recommend checking this out. There's a lot of great diagrams and walkthroughs of exactly what it says on the tin, the anatomy of a high throughput LM inference system, and specifically what vLLM has to consider to get a lot of the performance that it does. Features like continuous batching, prefix caching, and many other features that are really cool to see laid out like this. A bonus here actually is some of our friends at Modal, which is a nice serverless GPU cloud, just released their notebook feature. And Charles here released a notebook of his experience of kind of reading the blog and then also trying to dissect vLLM directly and look at what's the state of the engine. What if we pass in and schedule these requests, and then we step each request one token at a time and print out these things and really look at the guts of vLLM. So I recommend looking at both these things in parallel. It's a pretty cool way to understand a system like this both intuitively and very directly. So I think this is now one of the better ways to get a deep introduction into vLLM and get familiar with a lot of the systems that makes it work. Next, I want to share this blog from Thinking Machines about defeating non-determinism in LM inference. If you've used models from the closed source APIs or open source APIs, you're probably familiar with greedy decoding, sending your request in to a running batch of other requests, or just at a different time of day. You can get different results, even when the results are supposed to be deterministic. And Horace He, along with others at Thinking Machines and in collaboration with us, have been working on how to better support non-determinism in LM inference through an integration with vLLM, using these batch and variate ops that they've been working on. So it's a really cool blog. Recommend just reading it about LM inference and numerical precisions and why these things happen on modern hardware. And definitely let us know if you think this is like important for your use cases. Either evals or reinforcement learning. Where we definitely want to get this feature into vLLM as we can, effectively, having the option of trading off a bit of performance in order to get better determinism. Just recommend checking it out. And next, I want to share a release from Moonshot AI, the creators of Kimi, the Kimi models, or the like K1 and K2 models. They released this really cool project built on top of vLLM for efficient weight update and weight transfer between vLLM and their training harness, which is just really, really impressive for doing like trillion parameter scale weight updates in just a matter of seconds through really efficient, peer-to-peer updates. So if you're interested in reinforcement learning, hopefully you see a pattern here of a lot of the work on vLLM being geared towards that. Highly recommend checking out their project and write-ups about it. It's a pretty cool and elegant design. Next, or rather lastly, from my side, this is a pretty recent blog on the vLLM project on the how we support the Prithvi geospatial models. This is a bit of a unique model for vLLM because it's one of the first model architectures that features multimodal outputs. Here it is done in sort of like a plugin architecture, but obviously it's a bit of a growing moment for vLLM where we're not just considering token outputs. We're considering something else output from vLLM, and experimenting with how that's going to work out. So while it's maybe not a model you've been super excited about personally, depending on what you're working in, it is setting the foundation for and is a useful experiment for how we'll think about omni modality in LLMs in the future and how vLLM will grow to support those things. So yeah, I recommend giving it a try if you have any interest in multimodal outputs to see what the folks that have worked on it have come up with, and hopefully join the conversation that we're having in vLLM. So yeah, really excited for this. So that's all I have to cover today. And so I'm very excited to hand it off to our guest speakers to go deep in inference scheduling. Abdullah, if you want to take it away.
Thank you. Yeah, let me send. All right. You see my slides, okay?
Yeah.
Cool.
Yeah, good with me.
Yeah, hi everyone. I'm here on behalf of the llm-d team. I'm here with Kaushik and Neely. Kaushik from Google and Neely from IBM. So I'm going to talk about like intelligent inference scheduling with vLLM and llm-d. I want to be clear here that there are two types of scheduling. I know that vLLM itself does some sort of scheduling within the model server. This is not about that. This is about scheduling requests across model servers. And so you can think about it as also as load balancing. The other two, like other similar products that does this is like the SG-Lang router or the smart router that comes with Dynamo. So it's basically the load balancer with some intelligence of scheduling the requests across a group of model servers, backing the model server. And so why do we? I want to start by like some sort of motivations and try to justify why do we need some intelligence in the inference path, in the ingress path. As you probably mostly know, LLM inference requests rates are much lower than typical web traffic because they are a lot more expensive. But most importantly, also because the other most important characteristic is that they are non-uniform than typical services. The processing of a single request depends on like the context length, depends on the model itself, depends on how many tokens being generated. So they are significantly non-uniform. And because of that, traditional load balancing strategies such as random load balancing, round robin, are most likely going to lead to imbalanced scheduling, basically imbalanced load distribution across the model servers. And so we believe that efficient LLM scheduling or load balancing requires active management of the requests by the load balancer. It's not just because we want to have a better estimation of load on the model servers, because also we want to identify model server saturation points for a desired target latency. Typically, when we serve LLM requests, what we mostly care about is the latency, right? Like, for example, time to first token, time to output token. We also care sometimes about throughput as well. But depending on the application, you might care about latency. And to achieve a specific target latency, you want to load the model servers just enough to achieve that target latency. You can implement a bunch of optimizations like prefix cache tracking for prefix-aware placement. This is going to save you a lot. Again, stressing on the point that LLM requests are extremely expensive, and such optimizations can make a huge difference in your efficiency. They are not only expensive because they run for a long time, but also because they run on expensive hardware. Also, another example is LoRa-aware request scheduling. You could, for example, send the request to the model server that have the load adapter already loaded, and for example, in the accelerator memory. So this also can be done at the ingress layer, basically through the load balancer, or what we call here the inference scheduler. And last but not least, also disaggregated serving management. Disaggregated serving requires a fair amount of orchestration between the replicas, right? Like you've got the prefill and the decode replicas. You could have the inference scheduler, implement different load balancing strategy, whether you're doing the prefill phase or the decode phase. You also could have it involved in the orchestration itself, right? Like sending the request first to the prefill and then do the decode. I want to also stop here a little bit and say that this should be an interactive session. So if you have any questions, please feel free to interrupt me. And this is a quick intro why we need to have such a system like an inference scheduler in the ingress path. So we've developed something called like Kubernetes Inference Gateway. It's a Kubernetes native inference load balancer. This is a core component of the llm-d project. So the llm-d project built on top of the inference gateway. So when we talk about the llm-d inference scheduler, this is the top level. This is the component that within llm-d that depends on another component called Kubernetes Inference Gateway. As I mentioned, it's a Kubernetes native inference gateway. It extends what we're calling Kubernetes Gateway. There is, within Kubernetes ecosystem, we have a group of APIs called the Kubernetes Gateway APIs. Those are cloud agnostic set of APIs that capture users' intent to provision a load balancer depending on which provider you're creating this load balancer on. And so this is one of the biggest advantages of building such an inference scheduler or load balancer on top of the Kubernetes gateway. It's because it's cloud agnostic. And so, as I mentioned, we extend the Kubernetes native gateway API with a set of new APIs to express our intent to provision an inference load balance and inference load balancing strategies. We've also proposed a bunch of protocols. I'll talk about them in the next couple of slides to basically allow deploying this custom logic as a service. We've set a bunch of key design goals for this for inference gateway. One is maximum extensibility. You can either bring your own logic and deploy it. Those APIs are going to help you deploying it, and so you're going to have APIs that allows you to provision an inference scheduler, but you could bring your own, inference scheduling logic. You can develop it yourself, containerize it, and deploy it. And you'll use those APIs in a cloud agnostic fashion on any Kubernetes cluster to deploy it. And also, so this is one angle of extensibility. The other angle is allow you to extend the reference implementation. We have a reference implementation for the endpoint picking logic or the scheduling logic that is also extensible using a pluggable model. The other thing that I want to mention here is that this is focused on optimizing request scheduling for self-hosted models. So this is literally sitting in front of your vLLM servers. This is not trying to basically do semantic routing. It's not trying to pick, okay, should I send this request to OpenAI endpoint or Gemini endpoint, or send it to a self-hosted, for example, deployment. This is literally the one that is picking the model server that should be sending the request. The other product, usually referred to as AI Gateway, is something that could sit in front of what I'm describing here. And last but not least, a key design goal here is we want to have a clear path for integration with cloud providers. As I mentioned earlier, again, this is facilitated by having this project extending Kubernetes Gateway, which is a cloud agnostic set of APIs for provisioning load balancers. Any questions so far? Cool. So I quickly want to go over the inference gateway APIs. Those are the two new APIs that we propose to extend the Kubernetes gateway APIs. So the ones in black boxes, those are APIs that already exist in Kubernetes. So when you want to create a load balancer on a Kubernetes cluster, you create a gateway, and then you create an HTTP route that allows you to express, for example, which request should go to which service. And so we extended that with a new API called Inference Pool. And so basically, when you want to express the intent to create an inference gateway, you create an inference pool, which would allow the cloud provider to react and create a load balancer with an endpoint picking service, which I'll explain in the next slide. We also have a new optional API called Inference Objective. It aims to capture user intent in terms of latency requirements. This is a new API that I will talk about in the Kaushik will talk about in their prediction-based load balancing. So this diagram shows the high-level architecture of the inference gateway. Here I want to explain how we are converting a normal load balancer that you provision on any cloud provider into an inference gateway. And so the boxes in the yellow, those are things that get deployed or are involved in a normal load balancer. So a user, as I mentioned in the previous slide, could use the Kubernetes gateway API to create a gateway, and the load and the what we call here the gateway controller within the Kubernetes ecosystem would provision for you the load balancer, basically the L7 proxy. It could be an Envoy proxy. With the inference pool API that I mentioned, if that was the one that is being referenced as the backend, the gateway controller would basically create an extension here into an endpoint picking service. So what I want to stress here is that the traffic path would be as follows. The client would send traffic to the load balancer, the L7 proxy. The proxy is basically going to make a call out into this endpoint picking service, which includes the logic to pick an endpoint based on its understanding that this is an LLM inference traffic, and then return to the L7 proxy its pick, which exact model server this request should be sent to, and then the L7 proxy will basically obey and send traffic. And so what I was describing before is these set of APIs, as I mentioned, the inference pool and the protocols is what this project is trying to standardize within the Kubernetes ecosystem so that we make it cloud provider agnostic. And then cloud providers for example, Google, they could integrate this with their Google Cloud Load Balancer, AWS, the same thing. And you don't have to, for example, this is one of the, from my opinion, biggest differentiators between this and an SGLang router, for example, which is like a literal router or a literal proxy that you have to deploy on your cluster and you have to manage it. With this approach I'm describing here, it allows you to create, again, like an inference scheduler that integrates with a managed load balancing service that could be provided by your cloud provider. This also integrates with open source proxies, again, like Envoy, Istio as well, and so it gives you more flexibility to integrate potentially with your existing infrastructure. And any questions? Cool. I wanted to maybe just quickly, sorry. So the difference between AI gateway and inference gateway, that's what I described at the beginning, right? Like the AI gateway is, what we think about it is something that sits in front of inference gateway. AI gateway is a product that potentially could pick that your request should be sent to which exact model, for example, right? Like it does semantic routing, or depending on some cost analysis, it should send it to OpenAI endpoint or send it to your managed inference deployment. Inference gateway is strictly a scheduler or a load balancer in front of your model servers, self-hosted model servers. I hope that explains it. So I want to quickly skim through, the EPP implementation itself. Again, as I mentioned, this is the brain or the actual scheduler that the load balancer basically calls out into to make a decision on where to schedule a request. I don't want to go into details, but I just want to say that the main thing that you have here is a bunch of scorers, extensible scorers that you could implement and add to the existing reference implementation. And we will talk about at least 3 of them in the next few slides. Those scorers are the ones going to decide, okay, what score they should give to each of the each of the model servers that you have in the deployment. For example, it would score a model server with a shorter queue higher than one with a longer queue, or score a server with a longer matching prefix higher than another. So this is basically what the EPP would be doing. We've designed it in a way that is, as I mentioned, pluggable, and in order to allow you, for example, to keep also some state if you want, like tracking where prefix caches, which servers are maintaining which prefix caches, for example. Another thing I want to mention here is what this does is directly scraping metrics from the model servers, so that we have a fresh, a fresh understanding of the status of the model servers, such as as I mentioned, like queue length, KV cache utilization, and so forth. Even those are extensible as well. In this reference implementation, you could add new metrics that you want to scrape and you want to base your scorer on. Neely is going to talk about this as well. For example, you could look into prefix events or cache events to make a much more precise decision on where to send the request to based on prefix cache matching. Okay, so the first load balancing strategy that we implemented, and again, think about it as a scorer, is load aware. Traditional load balancing algorithms use number of requests, for example. You could use CPU utilization or GPU or even duty cycle. We've discovered that those are not very representative of load on the model servers. And so the upstream endpoint picker that we have includes a scorer for load aware scheduling based on KV cache utilization and queue length metrics scraped from the model servers directly. We have a simple heuristic basically based on thresholds for queue length and KV cache utilization. And we've shown that even such a simple approach would improve materially tail latency near saturation. So you can see here, like in the left side, for those two plots on the left side shows traditional load balancing. Shows the traffic grows gradually from left to right, and for the first graph shows KV cache utilizations on a group of model servers. So those are about like 1, 2, 3, 4 model servers. And then at the bottom, we show average queue length across those model servers. On the right, it's the exact same thing, but we're running this experiment with the gradually increasing the QPS through the GK inference gateway, or the Kubernetes inference gateway. You can see the difference here, like using such a simple heuristic would allow us to have a much more uniform KV cache utilization across the model servers. And this also, when I say near saturation, basically near the point where like the queue starts to build up. The queue starts to build up much earlier in the traditional load balancing. On the using the inference gateway or the llm-d scheduler, we did not observe queue building up. Of course, if we keep increasing traffic, increasing QPS, it will start. But I'm just trying to do an apple-to-apple comparison, and we stopped at the point where the QPS that triggered queue buildup on the traditional load balancing, and we show that we're able to handle that traffic without queues being built up. And queues being like built up impacts, for the most part, tail latency, or tail time to first token latency, which I'm showing here. So again, in this plot, we show on the left side, on the top, we're showing the average queue length. Again, it's the same as the previous plot, but in the bottom one, we show the tail TTFT. We show a spike again as queues start to build up, that we don't observe on the inference gateway. Hopefully that makes sense. I will next hand it over to Kaushik, who's going to talk about a bit more advanced scheduling strategy. Take it away, Kaushik.
Yes, thanks, Abdullah. So what we are working on in the next generation of load balancing algorithm is predicting the TTFT and teapot for a given request and a given server, and based on that, doing our load balancing. The way we have implemented it is, what I'm showing here at the top is basically what Abdullah showed. So we have a scheduler which has these scorers, and a request controller which dispatches requests and collects them back. And we have hooked it up with machine learning models. So basically, before scoring a pod, we get the predictions of the time to first token and time per output token of the request, and then we use that to determine which pod to send the request to, which model server, and also it gets trained online. So whenever a request comes back or a token comes back, if it is streamed, we send it to the same the trainer component of the models of the ML model, to get back to train the model, so that we do online learning of TTFT and teapot and use that for load balancing. So it does online, it learns online what a TTFT and teapot is going to be for a given request and a given server. Can you go to the next slide? Yeah. So how do we determine how do we train the model that predicts the TTFT and teapot? It uses it's actually quite not that complicated. We are using a XGBoost quantile regression model, because we are trying to predict the quantile of a particular TTFT and teapot. What's the, like, a given P90 or P95? So we use the metrics emitted by vLLM. So we are using KV cache. We are using number of requests running and waiting. We are using prefix cache score, which is the number, what is the overlap of the prompt and already that is cached in the vLLM. We are using input length, which is important for TTFT and not for teapot. And we can extend this list, but for now we have kept it to this. And this is being used. These are the features that are being collected and used to train and predict the model. Next. Next, I will show a couple of benchmarking that we did. So first, I will show a scenario where we have two workloads. Say we have a chatbot, which is based on the shared GPT dataset, and we have a coding workload where the user is trying to generate code with a different dataset. It's a Python code dataset. Both are in Hugging Face. And suppose we have different SLO requirements. So a chatbot, we have more lenient. So we want the P90 of time to first token to be 200 millisecond and the P90 of teapot to be 100 millisecond. For coding, we want a stricter SLO. So P90 is 100 and teapot is 40 millisecond. And these two workloads are sheddable in the sense if SLOs cannot be met, we are going to shed the requests. In realistic scenario, you can divert it to other pods and you can scale up the pods. But the idea is we want to maintain the saturation level of this pod so that it cannot cross these SLOs. And what I'm showing here is exactly that. So like right now using the KV cache and queue-based scoring, we are not really aware of the latency requirements. There's no easy way to determine whether the pod is saturated or not. But with this prediction-based routing, we can determine whether a given request, it is at a request level, we can hit the SLOs or not, and we hit the and we not let it cross. The pods are loaded such that it doesn't cross the TTFT and teapot. I'll answer the question. I have one more slide, and then I'll go to the answers. Yeah, and this is the same slide, but since we have two workloads, I'm now showing the chatbot workload, which can also achieve which also stays within the bounds of our SLOs. Can you go to the last slide? Yeah. Finally, I also want to show that even with a single workload which doesn't have any SLO, we can do a better job of load balancing compared to either naive round robin, which the Kubernetes load balancer does, or even a queue or KV cache based load balancer, because now we have a more granular understanding of a given request, what its TTFT and teapot is going to be. And if we are sending it to a pod that can that is least loaded, and now the load has no direct definition, it is based on the request and the pod, then we can do a better job of load balancing. And that is what I'm showing here, where using the prediction based load balancing, we get a better outcome of TTFT and teapot. There's a question on let me see if there's any. There are a lot of things going on, but yeah, anybody has any question? I have to, like, they want to speak up, or I will respond in the chat.
Kaushik, I have one question. Sorry, just to introduce myself. I'm Piyush. I'm a principal engineer at DigitalOcean. Just have a question around. We mentioned like two kinds of scheduling mechanisms. One is like queue based, and then the other is like prediction based. How much of a factor it is for prefix cache based routing? For example, like a prompt has been routed to a replica because of which the caches have been warmed up.
Yes.
In your benchmarks, is that a major sort of latency factor to be able to route to the same replica based on cache awareness, or it doesn't really matter too much?
No, it does. So prefix cache drastically reduces TTFT, right? Depending on how much of it is already cached. And the way we have solved the problem, so right now we have that as one of the scorer, and that ranks very highly in when we weight multiple scores. Prefix cache score has a very high weight compared to KV cache and queue scores. On the other hand, prediction based is something more holistic. It also takes into account the prefix cache to predict your TTFT and teapot. So it already has that as an input feature of the model and uses that for prediction.
I think Nili is going to talk about that in the prefix cache aware scheduling section, if I'm not mistaken. Like there are experiments that we show with and without load aware scorer. There's a difference. Like, of course, you have to prioritize prefix cache, but it's not only prefix cache aware routing. You have to take into account load on the model server as well. Clayton?
Something that's really important, I think, was kind of in some of these questions is there's a lot of different techniques kind of the approach we're taking now with the extensibility is to allow people to try one technique at a time and to kind of weigh them against each other. But in the long run, we want these to compose. And so a little bit of what Kaushik is working towards is you could imagine, for instance, something happening earlier in the processing pipeline, like the current scorer, that's predicting how many tokens will already be in the prefix cache. And then that subtracting for downstream scorers the number of tokens that a particular server is expected to actually have to answer. And then that feeding into something like what Kaushik is showing here as the more integrative model. And there's different approaches. People running in production might want to try one thing at a time. Someone looking for something that just works for a less important workload might prefer that integrative approach. And we're trying to work towards, getting those contributions and then stitching them together so that, for instance, all of us aren't just individually applying these hacks on the load balancers, but there's a single place where people can go to propose these and to pull them all together into a larger system.
Cool. Just in the interest of time, I'm going to go ahead into disaggregated serving quickly, so I give enough time for Nelly to cover prefix-aware scheduling. Sorry, you have hands up?
Yeah. Yeah, one small question regarding the endpoint picker. And when it meant endpoint picker protocol, like how does it pick an endpoint when a vLLM server is multiple servers in a single pod and multiple pods with one server in each pod? And what is the algorithm? How is it?
It doesn't matter, like from the endpoint picker perspective, those are independent model servers. Think about it like an even model engine, like the engine within vLLM. That's what we care about. Actually, like for DP, we are gonna have to be picking between engines within a vLLM deployment. And so those, again, those are independent endpoints. We don't care, right? Like those are, whether they are running on the same node or not, it doesn't matter. I think about it this way. For example, virtual machine, you could have created with 8 GPUs, or you could have created 8 VMs with a GPU on each, and then each one of them is running a model server, right?
Okay.
So I want to quickly go over disaggregated serving. llm-d scheduler with Inference Gateway implements disaggregated serving. This diagram shows the flow here, how Inference Gateway participates in picking the decode worker and the prefill worker. And so the Inference Gateway receives the request and it routes it to the decode worker, not the prefill. So and it basically picks the decode worker based on some scorers, part of what we discussed earlier, and then it will pick the prefill as well, but place it in a header. And this is what basically we will be sending to the decoder. We will be sending to forwarding the decoder the request. Basically the L7LP is gonna forward the request to the decoder with a header set for the prefill. The decode worker is going to do a remote prefill, so it's basically going to proxy the request to the prefill, run a prefill, receive back the KV cache memory block IDs and the first token, and then using Nixel, we're going to read the KV cache back, schedule a decode into a batch, and run the decode on the decode worker, and then the decode worker will return the tokens back into the Inference Gateway. So this is the simplest protocol that we managed to come up with that doesn't really require a lot on the Inference Gateway side or changes on the typical proxies that you have out there like Nginx and Envoy. From their perspective, they're basically talking to the decode worker. But behind the scenes, the decode worker is actually deferring the prefill to another worker that was picked earlier. And so this is one disadvantage of this protocol, is that we've picked the prefill worker much earlier. Because if the prefill we picked the decode much earlier than we should, right? So if the prefill takes a long time, then the decode worker that we picked might have become much more loaded, and so our pick could be suboptimal. And this is a topic for another talk. maybe. There is a proposal, Clayton and Rob, and others are working on. It's called disaggregated everything. We're trying to come up with new protocols, set of protocols, to not only disaggregate, like, the typical disaggregation that we're talking about here, which is between prefill and decoy, but also other aspects like, tokenization and whatnot. And here, this is showing an experiment that we ran with the llm-d scheduler on disaggregated serving. So the red line shows, basically using 4T P4. So this is basically using without disaggregation. And then the green one is splitting the same amount of resources between a decode worker and prefill worker. And you can see here as, like, traffic coming in increases per user output speed. We get better per GPU throughput difference, right? So we're pushing the frontier with this aggregated serving. So this is still early. Again, with our preliminary results, we're working towards other optimizations that would integrate with this and like YDP and data parallelism based load balancing as well.
Abdullah, maybe just go to the 2 slides before, because it is connected. Why are we splitting the prefill and the decode? The prefill phase is the phase where vLLM actually computes the KV cache values, and this is compute bound. The decode is actually generating the output tokens. So we need those KV cache values, having them and knowing they can be reused, by the way, meaning if a vLLM already calculated this prefix and we are now sending a request with the same or similar or subset of this prefix, we can reuse those KV cache values and basically save some of the computation. So part of the decision here of whether, and this is another example of the plugability of the inference gateway scheduler. We have a scheduler here that does this disaggregated serving, is making a decision. And how do we know, do we need to split the computation to prefix and decode to 2 vLLMs? We need to look at the prompt and look if we have enough of this prefix already cached. If we have it cached, basically we don't have much prefill work to do, and we will not split the computation. But if we don't have these cache values, we need to do a lot of prefill work, and we will decide to split it. And this is, of course, configurable, the amount of which we are making this decision. So why is KV cache very important? And being KV cache aware, this is part of the motivation. You can go, please, do our 2 slides ahead. So prefix aware scheduling. As we said, the ability to go to a vLLM pod where we already have these KV cache values or part of them, basically reduces the time to first tokens and maximizes the resource utilization. We have more KV cache sheets, and the time to first token will be better. So what we have here is prefix aware schedule, and you need to understand that these scores is not that you can use several weighted scores. It doesn't mean that you have to use one. You can use this prefix aware score and load aware score. So we have 2 types of prefix aware scores, one in the upstream inference gateway, and one that was developed in llm-d. The one that is in the inference gateway basically tracks and does estimation of where the KV cache values, where the prefixes of the model servers should be. How can you know where they are supposed to be? Because we know the prompt, we know where we sent the request. And if we are now getting a prompt that has some similar prefix, we take the longest and we say, okay, this pod will be scored. We have a higher score than one that has a smaller prefix or has none. So this is something that allows us to send the request to a pod where the KV cache values are there. But again, we need to understand that we do not want to send, assuming that you have a workload with a heavy prefix intersection, we still do not want to send all the requests to this pod. We also need to look at the load because we want to spread the request. So we need to do some weighted scoring. So as you can see here, this is some comparison between a prefix scorer and a prefix with a load-aware scoring, meaning we are using two scores. And as you can see, when we have a workload with heavy with a lot of matching prefixes, we would like also to use the load scorer in order to get better results. So this is one example. Let's move on to the second slide, talking about the precise KVK scorer. So what's the difference? When I said that the upstream inference gateway has a score that does estimation, we don't know if these KV cache values are still in this vLLM pod. And what was implemented by Maroon, that is also in this call, is a precise prefix scorer, which actually listens to the KV events. This is something that a vLLM emits. It was contributed by Dynamo. The KV events, and what we know now is also tracking if these KV cache values were evicted and are not there. So we have a precise KV cache score, and as you can see, there is a comparison here between a simple load scorer, a random picker, the estimate prefix aware score, and the precise score. And as you can see, the time to first token, there is a significant difference when using the precise in comparison to the others, also to the estimation, and the total throughput is much better. So we are having really great results with this precise score. Let's move on to I think, any questions? We do have a minute. Someone asked a question. This is something that we are working now on the data parallelism aware scheduling. This is under development. vLLM will now support basically multiple vLLM engines inside a single pod, exposing several ports. So we need some external load balancer. We want to leverage the scheduler in order to basically the entire scoring mechanism to route. Now we don't have just a single port, a single point of entry in vLLM. We have several. So we are scraping all these ports, getting all the matrices. And the inference pool was also extended in the last release to have multiple target pods. And the scheduler is now aware of basically the status, the KV values, the load of each one of these API servers, and we are able to route directly to a specific port in a pod. It's one pod per node. I think we are out of time.
Thank you. Maybe hand it over to Michael.
Yeah, thank you very much. Great presentation, folks. We're obviously at time, but there's been a lot of great questions all throughout. Are there any questions people have remaining or would like to come off mute to ask at the end here? Okay, well, there's two questions that came through in the comments. Is vLLM's data parallel deployment strategy clash with KV cache aware scheduling?
No, it does not, because we are now KV aware for each. That's what I was saying. We are now scraping and have this information for each of the ports, each GPU. We know the KV cache. So we have load for each, we have KV cache aware for each, and we are able to leverage the scheduling for it. So no, it helps, and we are leveraging it as an external load balancer.
I just posted a link to the community. Please consider joining the Slack channel there, ask more questions there, and engage with our with the larger llm-d community.
Yeah, thanks. Okay, yeah, there was that last question, but Maroon already got to it. Yeah, well, I think we're doing great here. Thanks so much for the active questions and commentary in the chat. Yeah, and appreciate everyone coming out for this week. Look forward to seeing you in the next 2 weeks. Yeah, please join the vLLM and llm-d community and help us get to cluster scale in more clusters. Thanks everyone. Have a good week.